Good morning, everyone. Thank you for being here. For the next 15 minutes, I want to talk about a single piece of hardware that's more than an algorithm or a data set, and that has quietly powered the entire modern AI revolution, the graphical processing unit. Everyone knows it's the GPU. We'll look into it, why it matters, how it fits into the machine learning so accurately, and how it actually works on the inside, where it shows up in the real world, and where it's all heading towards. So let's get into it, right? So AI appetite for compute. Here's the backdrop. Every major leap in machine learning lasted over 10 last decade has been overshadowed by the leap in compute. The graph or the chart shown on the right shows the estimate training compute of the landmark models, and notice the axis on the left is a log scale. So each step is roughly 10 times more compute than the one below it. From AlexNet in 2012 to GPT-4 class model today, that's on the order of 100 million fold increase in the raw compute itself, right? That curve simply would not exist without the parallel hardware to ride it, and the economics follows the compute. For a large language model, the overwhelming majority of the cost, often 80% or more, is the GPU time. So when we talk about the progress of AI, we are to the surprisingly degree talking about the progress of this one chip. And that's why it's worth understanding. So the difference between a CPU and a GPU, to understand why, start with a contrast, right? A CPU and a GPU represent two different philosophies of computing. A CPU has a handful of very powerful cores. It's optimized for latency, for doing one complicated thing, then the next thing very fast with big caches, clever branch prediction mechanism. Think of it as like a sports car where like you are like perfectly aligned to winning a race, brilliantly for getting a single passenger somewhere quickly. A GPU on the flip, basically instead of having more powerful cores, it has tens of thousands of simple ones. It's optimized not for latency but for throughput, for doing the same operation across enormous amount of data all at once. That's the fleet of delivery van. Each one is slower, but together they move a staggering amount of cargo. Neither is better. They are built for different jobs. Machine learning happens to be exactly the job of what GPU can do well. Why ML loves GPU? So why is the love between the ML and GPU, right? Because underneath all the buzzword, a neural network is almost dense linear algebra. Training and running a model comes down to multiplying big matrices together. Billions of identical multiply and operations, and critically, each of those operations are independent. The technical term is embarrassingly parallel. Every output can be computed at a single same time with almost no coordination. That maps perfectly onto 1000 or like maybe a lakh of cores. GPU run this with the model called SIMT, single instruction, multiple threads, where one instruction is delivered multiple threads in lockstep. So you are not wasting energy on control logic for each data point. And that's the beautiful trick at the heart of it. While some threads are stuck waiting on the memory, the GPU just runs the other threads. It hides the latency with the sheer amount of work, the workloads, the hardwares are quietly simple, a perfect match for the AI workload. Let's open it up, right? A modern GPU is really a hierarchy of repeating tiles. The main tile is called the streaming multiprocessor or the SMs. A top end data center GPU has well over hundreds or thousands of them. Inside each of these SMs, you will find thousands of CUDA nodes or cores, the general processing or the arithmetic unit, which is the bulk horsepower. You will also find the tensor cores specialized for doing matrix multiplications or matrix maths. We will come back to them at a second because they are the secret sauce or the recipe. And the wrapping up all in the memory systems from tiny fast registers out to the large pool of high bandwidth memory. So compute tiles fed by the memory piles hold these two ideas, compute and memory, because the next two slides are the ones which will talk about those. Tensor Core. First compute Tensor Core arrived in 2017. They are the single biggest reason GPUs got so much faster for AI specifically. A normal code multiplies two numbers. A tensor code does the whole matrix multiplication, multiply and accumulate in a single shot. It fuses a pile of these multiply and add into a single operations. Thousands of stack of them work together, and the throughput is staggering. Look at the jump across the four generation: V100, A100, H100, and the Blackwell B200 in 2024. That's roughly eightfold increase in the raw matrix throughput in about 7 years, far faster than the old pace of chip improvement. And that's the trick called structured sparsity that can nearly double the effective rate again by skipping zeros. This is the engine room for deep learning. The memory and the bandwidth wall, that's the catch. And its most counterintuitive idea in the talk: modern GPUs can multiply faster than they can fed. The math unit are so fast, very often the bottleneck is in the compute, it's the moving the data. The pyramid is the memory hierarchy. At the top, the registers, the tiny but lightning fast registers sit. Down there are L1 cache, shared memory, L2 cache, a bigger and a slower cache, and then there's a bottom pool of the high bandwidth memories and the HBMs and others, right? Tens of gigabyte feeding into a chip at multiple terabytes per second. That sounds enormous, still isn't always enough. The golden rule for anyone writing a GPU code is keep data close. The whole craft of fast ML kernel is reusing the data on chip instead of constantly going back and bringing the data again and again. Performance today is the data movement problem as much as the math problem. The numerical precisions, one of our powerful levers for both of these are compute and memory, is the precision, how much data we use to represent each number. Fewer bits means that you can move the data, multiply more number of data per second, and fit bigger models in the same memory. So some model ML climbs a whole ladder of precisions. Full 32-bit can be encoded into maybe 16-bit or maybe 8-bit or 4-bit at the cutting edge technologies. The clever part is mixed precisions. You compute in low precisions, accumulate at higher precision. So when you get into the speed of the low precisions with a little loss of accuracy, and for deployment, we quantize them into maybe a 8-bit integer to make the models cheap and fast. The direction is left to right, and the trade is the accuracy for the cost of speed. The software stack now, almost all anybody in the room who programs GPU by hand and who doesn't have to because of the software stack, at the very bottom sits the CUDA level, which has bunch of libraries: CUDA NN, CUBLAS, NCCL, and multi GPU communication. There are the runtime like the Triton, the XLA, the Tensor Cores, and at the top the framework sits the PyTorch, TensorFlow, ZAX, and other training parameters. Each layer add convenience without giving up the speed. And one strategic point worth flagging: the mature CUDA ecosystem is a huge part of why companies dominate the hardware. The chips are excellent, but the software mode is very important. For the largest model, even the biggest GPU isn't enough. The model doesn't fit. Full stop. So the training spreads across thousands and multiples of GPUs. Data parallelism copy model onto many GPUs, split the branches of data between them, average the results. Tensor parallelism take a single layer that's too big and splits into multiple metrics across the GPUs that compute together. The pipeline parallelism puts the different layers of GPUs and stream batches through like a assembly line. It practices you combine all the three, but none of them works without plumbing ultra fast interconnect, which is the links and the switches and the bands and the interconnects, which basically across the cluster, so that the thousands of chip can behave like a giant accelerator. The application across ML includes a vast variety of the world is currently seeing: the computer visions, classification, detection, medical imaging, self-driving cars, the language models behind the chat, transitions, code, speech, audio in real time, generative AI, the diffusion models and the transformer models making images, videos, 3D recommender systems, the giant models ranking your feed, your ad, your shopping and science behind the protein folding, the climate modeling, drug discovery, and physics, completely differently fields, but underneath the substrate is doing the heavy lifting. The GPU is the common engine undergone. So with that, I will basically end my talk. Thank you.